This is the video for the BE1500 group with Meg Darrow, Madison Horsch, and Nick Atovski. We chose to do our project on the global land temperatures dataset. According to NASA, global warming has occurred at a heightened rate over the past 35 years. We wanted to show that our data reflected these findings. We also wanted to show a couple of odd cases, if you will, cases that make people like Jim Inhofe question perfectly good science. If you're wondering who Jim Inhofe is, that's the guy who took a snowball onto the Senate floor to prove climate change doesn't exist. Yeah, that guy. Anyway, we were sure that there were microcosms in our data that showed decreasing temperatures, and we wanted to display those to show that one place in the world with decreasing temperatures does not, in fact, negate the existence of climate change. Our dataset included a few Excel files, including data by major city, country, and global land and ocean temperature. We used the land and ocean file and the major cities file. Without further ado, let's get to the first function file. Okay, this is our first function file called nationtemp. It takes input of country, and you can enter any country that's included in the dataset within single quotes as per MATLAB syntax. There's no outputs because all of the outputs are plots. So we are just going to go line by line. The first line that's not commented out is an fprintf statement, and that just displays into the command window that you have entered this country into the nationtemp program. This program will now format the data pertaining to said country and output graphs of the data found. This may take some time. It's not kidding. This takes quite a bit of time because this Excel spreadsheet is over 230,000 lines long, which is an improvement considering that the city Excel spreadsheet was over 1.5 million lines long, and that took about 20 minutes to run. So, here is the XLS read line, and it says global land temperatures by major city, and it outputs the data into a number matrix and a text cell array. So, and then this is just saving all of the data. So we have the raw temperature, the raw date, the raw city, so nat raw is the raw nation. TL is the length of the temperature, the length of the date, the length of the city, the length of the nation, and then the latitude and the longitude. And then the month is just numbers from 1 through 12. Now we're taking the size of the text file to make sure that we don't go over the expected dimensions. And this is from 1 to the length of the date. And it says up here that this data set is extremely long and that there are formatting discrepancies with the dates throughout the set. This short segment goes through every date in the date raw vector and extracts 4 numbers corresponding to the year and stores those in another vector. Now there are 2 different formats that are used intermittently throughout this data set, and one of them includes slashes and has the year last. The other one includes dashes and has the year first. So this for loop and nested if statement, or if statement nested within a for loop, includes a couple of commands that help find where the actual date is. So I'm using the isEmpty command and then strFind, and the strFind goes through any string that you have, and if it finds any character that you have in quotes here, so that could be a string of characters or just one character, then it actually outputs a vector with the positions at which those are found. So what I have here is if isEmpty strFind date raw at position I, so counts from 1 to the length of the date, and then a slash. So that's saying that if you don't find a slash, there's only 2 cases. Like I said in the data set, there's only 2 cases. You can either find a dash or you could find a slash. And if you don't find a slash, then that means that you have to have a dash. And if you have a dash, that means your year is first. So then it says year is str to double date raw from 1 to 4. Like I said, you would find the date first. And then there's this else if statement, if is empty. If you don't find a dash, then you will have found a slash, and that means that the year is last. So, and then this says, this is basically the vector that is displayed where you would find the slashes. Remember how I said it's the position at which you find the slashes? So, and then this is the line of code that saves the year, because the problem with the slash format is that it doesn't include zeros before any single digit number. So it's not 0, 1, it's 1, 10, 2015. It's 2, 10, 2015 instead of 0, 1, 0, 2, which means that the length changes. So I can't just put a number here. It has to be a floating value depending on whether it's a single digit or double digit number. Now on to the next portion. This segment cuts, hence the variable names, the data down to only the data pertaining to the specific country entered. So this is, we're just initializing a count value here, and then we go through a for loop from 1 to m. And remember, m up here we classified as the size of the text file. So we're going through the text file, and we are searching for the country within the column of the text file that is the nation. And if it finds it, it saves the cut vectors as whatever is in the other columns. So whatever pertains to the country gets saved in these temp cut, nat cut, date cut, and year cut vectors. And then this count value goes up by 1. And the reason that this isn't the same as this is because this just goes from 1 to the size of the text file, and I2 isn't going to go up to the size of the text file because the text file is going to be significantly longer because it has all the countries in the world. This doesn't have all the countries in the world, it just has 1. So what ends up happening is you end up getting a vector that counts from 1 to whatever your value is. Now if I put j here, what you would end up seeing is you would see a whole bunch of blanks, and then it would get down to, I don't know, 15,000 or something, depending on the country that you entered, and then you would see a bunch of data, and then it would be gone again, and there would be a whole bunch of empty areas. So we obviously don't want that. We want it to go from 1 to whatever length it is. We don't want any empty spaces because that messes with graphing. So this is how we get around that, by initializing a second counter. So then we take the length of all of those vectors that we have created, and then we go on to the next segment. This segment matches the years and the temperatures and makes them both into vectors of the same format. Now, this is a little difficult to understand, so I'm going to explain it real slow here. So we're initializing a second counter here, just like what we did above, and then we are going from 1 to the length of the cut temperature vector. And this is taking all the data that's only between 1950 and 2012. Now, the reason for this is I specified at the top that the data set is extremely long and there are formatting discrepancies throughout the set. There aren't just formatting discrepancies, the formatting itself is egregious. And if you would take the time to look at it, you would see what I mean. According to the project statement, we were not supposed to deal with the Excel document at all, so I had to code my way around it. I had to jump over the egregious formatting. So, this is how I'm doing it. There were gaps in the data. Depending on which country you chose, there could be more gaps or less gaps. If it was a third world country in Africa, there would be typically more gaps because the temperature data obviously wasn't going to be that reliable. But we found over the course of the data set that the years from 1950 to 2012 were generally pretty reliable. So this is taking all the data from 1950 to 2012 and saving the year, and then saving a new temp cut vector that displays, that only has a temperature from 1950 to 2012. And then this is just the counter. And like I explained above, this is so it starts at 1, this is so the data starts at 1 and it doesn't start at like 500 or something. Okay, so now we go on to the next segment. This just makes sure that the temperature vector can be reshaped, and the reason I'm reshaping it is I want a temperature matrix. It's going to be 12 columns, and X number of rows. Why do I want it 12 columns? Because there's 12 months in a year. And if I want to take a yearly average, the best thing to do would be to reshape this vector into something with 12 columns and take the average of each row. So, the easiest thing to do is to reshape it. And there is actually a reshape command in MATLAB. Thank you, MATLAB, so helpful. And you can actually just type in the dimensions that you want your matrix to be. In my case, it's the length divided by 12, comma 12. So every row is a year. And this just makes sure that the temp cut vector is some number that's divisible by 12. Because there could be the odd, there are actually odd data points that slip through here in some cases, because it'll do 1950 twice, or it'll do 2012 twice. Like, it'll go back through the data and it'll find another 1950. So this is just preventing that from being an issue later on in the code. And then here is line 81. As I said, this is just reshaping the temp cut vector. This is taking the size of that temp shape. So temp shape is my reshaped temperature vector right here. And so we've reshaped it, and then I'm initializing another counter again. And then we go from 1 to the number of rows, and then we do a couple of different things here. So we take the average temperature, the maximum temperature, and the minimum temperature. And all of this data is going to be more useful later on. And then this line of code is just matrix division, and it'll just give you a random number depending on what country you entered. And we haven't really used that actually onward, so I'm probably going to end up commenting that out. Here we have, so this is actually a second function. So if you see here this cell too far, this is calling another function. So we're going to go up here, and this is the cell too far function. And it does exactly what you think it is if you can divine what it is from the name. Cell too far takes input of a vector or matrix and changes the values to Fahrenheit. So all the values in our data set were in Celsius, and I wanted to be able to display them both Celsius and Fahrenheit, because depending on who is looking at the data set, one is going to make more sense than the other, and I wanted them to be able to see both. So this is just taking the size of whatever you entered, and then this is just a nested for loop that just goes through the size of whatever matrix or vector you entered. It can be a matrix or a vector, it doesn't matter. And this just does the requisite steps to change from Celsius to Fahrenheit, and that is multiplying by 1.8 and adding 32. So we go back to our nation temp big long function file, and you get out 4 different vectors. Temp var, that's all the data points. And then EVG far, that's of the average temperature, minimum, and then maximum. And now this is the good part. Now we get to graphing all the data. So this here, I know it's a lot of lines, but this will actually only output one figure, because I have a figure command up here, and if you just type in figure to MATLAB, it tells it to open a new figure. And then I have a bunch of subplot commands. So this plots the maximum temperatures and minimum temperatures in degrees Celsius and degrees Fahrenheit. So that'll give you a tiled graph of maximum and minimum temperatures in both Celsius and Fahrenheit. Then we open up a second figure, and we do subplot there, and that displays the average temperatures in both Celsius and Fahrenheit. And then this is a third figure, and this is my personal favorite. This outputs a histogram of the most common temperatures from 1950 to 2012. So it'll show you kind of almost, if you will, a true average of what the temperature in that area would have been, because this is the temperature that occurs most often in the data set. So we have 2 subplot commands here that'll tile the data in both degrees Celsius and degrees Fahrenheit. So we're going to run the program now, and I am going to enter Germany. So without further ado, here we go. So this is just calling the function in the command window, and I have to enter Germany in single quotes as per MATLAB syntax. Now, cue Jeopardy theme song. This is just explaining what you have entered into the command window. You have entered Germany into the nation temp program. This program will now format the data pertaining to Germany and output graphs with the data found. This may take some time. So, sit back and relax, have a coffee, and we're going to wait for this to be done. And we're back. Okay, so here we have figure 3, here we have figure 2, and here we have figure 1. Okay, you see how the text is overlaid onto itself and you can't really read it? Don't panic, we'll fix that. Alright, we are going to resize this to just a little bit easier to see, and this is the tiled graph that I was talking about in the first figure. This is the maximum temperatures per year and minimum temperatures per year, and they're tiled based on columns. So degrees C is on top and degrees Fahrenheit is on the bottom. And you can see it's kind of all over the place. But something that you can notice actually that I found a little bit interesting is if you take a look at these spikes. So according to NASA, the science for global warming actually started out as global warming, but now the consensus is that we're actually calling it climate change. And climate change is the idea that the highs get higher and the lows get lower, and the weather gets crazier. So if you take a look at this, the highs, these peaks here, they're actually getting higher. So that makes sense. That goes along with the findings. And then you go over here to these minimum temperatures and see all these spikes. Ooh, whoa, that's really cold. Ooh, man. 1988, they had a bad year, man. Okay. You see in the 2000s here, we're actually, these spikes are actually going down. So the lows are getting lower, just as we expect to see. So that's as expected. That's a good finding. We can work with that. So we go to the next figure. Sorry if I can find it. Alright, here it is. Ta-da! Oh, see? Fixed it. No overlaid text. Now, so take a look at this. This is actually really interesting. And this kind of explains why we have people like Jim Inhofe. Remember I explained who Jim Inhofe was at the beginning of this video. So here we have the tiled average temperatures from 1950 to 2012, degrees Celsius, degrees Fahrenheit, and if you want to look at the numbers, if you want to look at Fahrenheit, because we're Americans, you can look at the Fahrenheit, it might make a little bit more sense. So, let's see, that looks like 1979. The temperature went way up to like 52 degrees, and you might be saying that that's a really low average, but keep in mind that that's a yearly average. So that takes in winter and summer into account, so the winter is obviously going to drag down the summer. And Germany actually is pretty mild for given where it is, because it gets wind off the ocean, and it actually cools it down quite a bit. So let's look at the average temperature here, and I guess if we were to draw a line here, it would look kind of like an upside down parabola, but let's just go from 1980 onward. So you go from 1980, and if you look at the middle of the data, it's actually trending downward. So that's interesting. I thought that global warming meant it was supposed to be trending upward. Well, yes, that's technically true. But if you remember the picture that I showed at the beginning, that's a picture of a time lapse that NASA did of the global temperatures, and it shows that the Earth has actually gotten warmer. So that's a proven fact that places are getting warmer. But if you notice, there were actually pockets of blue still on that picture. So it was like what I said at the beginning. Just one little area of decreasing temperature doesn't entirely negate the existence of climate change. In fact, it doesn't really negate it at all, because if you think about it, this is just taking the data from one latitude and latitudinal and longitudinal point. In this case, it would be Berlin, Germany, I think, is what's in the data set. So it'd be taking the data from Berlin, Germany, and just plotting that. And that data could very well be going down, because Berlin, when you think about it, when you think about the whole planet, Berlin is a tiny area with a lot of people in it for sure, but a tiny, tiny area. And so it makes sense that something like that might be going down while the rest of the Earth could actually conceivably be going up, because it's such a small pinprick area. It's like what we said at the beginning, it's a microcosm. So it's far from representative of what we would find when we took average global temperatures. So, if you want to take a look at the histogram, this is probably my favorite. So this it tallies the number of occurrences of each temperature, and it gives you kind of a degrees C's case, kind of a bell curve looking thing. So we have, between 8.5 and 9 degrees Celsius occurred almost 25 times. So if we look here, that's like 47, 48 degrees Fahrenheit. That occurred almost 25 times. So that gives you an idea of the kind of temperatures that they're experiencing in Germany most of the time. So that is the explanation of my function file. That is just about what it does. We input a country, it goes through a very large data set with an egregious amount of formatting errors, and it spits out a whole bunch of graphs that you can look at and you can peruse at your leisure. And as I have explained, I think the findings are actually very, very interesting.
This function file reads data from the global temperatures XL file and stores it into the variable data. The purpose of this function file is to plot the average land, maximum land, minimum land, and average ocean temperatures over the last 65 years and find out how much that temperature has changed over that time period. The first column in the Excel file is the dates. The time variable is set to that column. The line underneath it sets time to time being formatted in a more readable format that is easier to graph. Av land is the average land temperature data. Max land is the maximum land temperature data. Min land is the minimum land temperature data. And Av ocean is the average ocean temperature data. X is a counter used to make AAV, BAV, CAV, and DAV vectors of the right length. The for loops take the average of every 3 years or every 36 months. AAV is the average for AV land. BAV is the average for maximum land temperature. CAV is the average for min land. And DAV is the average for Av ocean. X increments by 1 each time through the loop to create the vectors. X is then reset after each loop, otherwise the vectors would be bigger than the last and would not be graphable. Time A is every 36th value of time 2 until the length of Av land is reached. This creates a vector that is the same length as Av A and has the right dates. Time B is for BAV, time C is for CAV, and time D is for DAV. A diff is the difference in the newest and the oldest data for the average land temperature. B diff is for max temperature, C diff is for min temperature, and D diff is for ocean temperature. Figure creates a new window for graphs so that they don't accidentally override each other. Using subplot, the code graphs all 4 of the following graphs on the same window. The first 4 graphs using the first subplot are time versus average land temperature, time versus maximum land temperature, time versus minimum land temperature, and time versus average ocean temperature. The next 4 graphs using the second subplot are every 3 years versus the average land temperature average, the maximum land temperature average, the minimum land temperature average, and the ocean temperature average. The next graph is average land versus average ocean temperatures average. This is to see if the land and ocean temperatures are changing in a similar way. And the last thing that the code does is tell the users exactly how much each variable changes over the last 65 years, and it uses fprintf to do this. The only thing the user needs to type into the command window is the file name, which is project2f1. And this is case sensitive. And then you press enter. The first graph that you see is land versus ocean temperature average. As you can see, there is no correlation to one another. They either increase or decrease independently of one another. The next window is the average temperature data for all 4. As you can see, there are several highs and lows, but overall the temperature has not changed that much. The last window has the original data graphed for all 4 of the variables. As you can see, it is very condensed. This leads to taking the average of every 3 years. Look in the command window, which is down here. You can see that each of the temperatures have increased over the last 65 years, even though they are all small amounts. Average land temperature, 1.13 degrees Celsius. The average maximum land temperature has increased by 1.01 degrees Celsius. The average minimum land temperature has increased by 0.38 degrees Celsius. And the average ocean temperature has increased by 0.088 degrees Celsius. This data shows that even if it is only a little bit, the average temperature is increasing over a long period of time.
So this is my portion of the code, and it looks at average temperature of all major cities from around the world. The user has the ability to input 2 major cities, and it will make sure that they were inputting correctly. It will display an error if not, and it will display the list of major cities the user can input. It will grab the temperature for each individual city, all the temperature data points rather, and then it will determine which city has the greatest average over the 62-year time span. Finally, it will plot a bar and scatter plot for each. My variable names are as follows. MC is my unique major city list. X is my first input. Capital X is my second. AT is my average temperature. V is my average temperature for the first input, and Z is my average temperature for the second input. Data1 is my other variable, and that reads my entire data set off the Excel spreadsheet. And as you can see here, that's my Excel spreadsheet. I want to display MC, so in case the user does input something incorrectly, it will still have the ability to scroll up and find out which city will work. And then I use length to see how many values I need to cycle through in order for the code to only grab the data I need for that major city that was input. This compares if the city was input correctly, and below will display an error if it's not. And then it will display the major city list again, just so the user has the ability to scroll up. This is how I captured my average temperature data, and I'm going from 1 to 12 all the way until the end of my average temperature, incrementing every year, and this captures my temperature for only that city entered, and this captures the average temperature for that city. And then it increments until I have all my temperature. I'm using this to calculate the number of years. This just displays my data from 1950 to 2012. And this portion of my code is the same as the above, just for the second data point, capital X. If I scroll down, I have subplots for 2 bar graphs and 2 scatter plots. My inputs, my titles are whatever my user will input. This will sum up my temperature for the first user input, and then this will take the average. And then for those, it will display the averages of both, and then it will compare which one has a greater average. So for example, I input 2 major cities that I know are on my Excel spreadsheet and will work and are spelled correctly. So once I run the code, which will take some time, I will show you guys exactly what it displays. So it will display all my major city names. It will display the averages I entered, and then it will display which one has a greater average over that time frame. Now here it displays my graphs, so my 2 bar graphs and my 2 scatter plots. And as you can see on the side, like I stated before, V is the average temperature data for the first input, Z is the average temperature data for the second input, and uppercase V and uppercase Z are the time frame from 1950 to 2012. So for example, let's say I still did X equals Kabul. I still entered that incorrectly, but I misspelled Paris. And I ran my code again. It will still take some time because my first input was put incorrectly, so it's going to sift through all the data. Once that's done though, it will display an error, not a major city, try again with the above. So the user can scroll up and actually see what the code will do. For the most part, that is my portion of the code.